In this video, we'll learn about radical reactions and how to write their mechanism. When we first think about radical reactions, it's important to know that they're not as common as polar reactions. Most reactions we see with organic chemistry are polar reactions. There's only a few radical reactions that we tend to see. And radicals react to complete an electron octet of a valence shell. So here we have an unpaired electron. That unpaired electron is going to react with a compound so it can have a full octet. But now you see we have another radical here. And so a radical can add to an alkene to give a new radical, which is how we can cause an addition reaction sometimes. When we're looking at the mechanism for a radical reaction, there are three different steps. First, we have initiation. That's the start of our reaction. That's when we first create the radical. Then we have propagation. Propagation is where we continue the radical by moving it to a different compound. So this is where the radical will start jumping between different compounds. And termination is when a radical reaction ends. So that's where two radicals come together. So now let's look at all these steps in more detail. Step 1, initiation. This is where we have homolytic cleavage. That's where we take the electrons that form our bond and we split them apart onto two atoms. So this way we create two radicals. So let's say we have chlorine and we react it with light. If I take my chlorine and I react it with light, that'll cause a homolytic cleavage. So that'll cause one electron to move to the chlorine and another electron to move to the other chlorine, which gives us two chlorine radicals. This is our initiation step where we first create that radical. And it tends to be the halogens that we most often see starting initiation for radical reactions. Next, we have propagation. Propagation is where the radical moves from one location to another. It moves from one molecule or atom to another. So here you can see a couple different types. We can add to the pi bond of an alkene. We can take a hydrogen from another compound. We can take a halogen from another compound. Or we can eliminate off a functional group from a compound and create an alkene. So all of these are different types of propagation steps. But as you can see, we start with a radical and we end with a new radical. And this new radical can go on and continue to propagate that radical. So this radical here could react with something like this to add a hydrogen and still create the radical R here. So if we look at that propagation step, let's say we had our chlorine from our initiation step, and we have methane. What will happen is the chlorine will go and abstract a hydrogen from methane. And in the course of this propagation step, we've created a methane radical. So you can see here, we start with a chlorine radical. Now we created a methane radical. So this would be considered a propagation step. That methane radical can then go and react to create more radicals. So we can have our next step with our methane radical. And let's say it runs into some chlorines. That radical can then go give me chloromethane and a new chlorine radical. And so with radicals, you only need a little bit of radical to start what we consider a radical chain reaction. So you can see I started with a chlorine radical, created a methane radical. That one then went and reacted with more chlorine to give me chloromethane and a chlorine radical. This chlorine radical can then go and restart the reaction again. So once you have a radical reaction started, it can keep going and going. You don't need to keep adding light into it over and over. So then our third step is termination. Termination is where two radicals come together and eliminate the reaction. So here, let's say our step one, just to review. And so when those two radicals come together to eliminate, you can create new products. So now let's put all three of these steps together and really look at termination. So step one was propagation. So step one was initiation. That's where my two radicals in the presence of light that's where in the presence of light, I first create my radicals. So that's where I first create that radical chlorine. Then our next step is propagation. So that's where my radical will then go and create new radicals. So if we had our methane, it will then go and react to create the new one. And that gave me my methane radical. That methane radical can then go and keep reacting till we come back to that chlorine radical to start with. And so as you can see, that chlorine radical is down here. It's the same as I started with. So I'm done with my propagation steps. Then we go to termination, where we take two radicals and they combine together to create a product. So we end that cycle of forming a new radical. And this is why I wanted to redraw the first two steps for you. Because in termination, what we're going to do is look for all the different radicals I have drawn in propagation and combine them together. So I can take the chlorine here and it reacts with a methane radical. So if my chlorine radical reacts with my methane radical, I end up with a chloromethane. My chlorine radical can also react with another chlorine radical. And when they react together, you just get that Cl2 back. And then another possibility, if my methane radical reacted with another methane radical. That can happen. So when that happens, we end up forming our new product, ethane. And so what happens is we have 3 different termination products. By far the most common one will be chloromethane, because we're creating it during propagation and during termination. And then even if we create Cl2, that gets used up during propagation. We'll have a little tiny bit of ethane at the end. Not much, just a little bit. But most of the product would be this one because it's also created during propagation. And so when we write our mechanisms for our radical reactions, we want to include all 3 steps. And it's good to kind of list them out like this, where you label it initiation, propagation, and termination. But remember, when you're doing your mechanisms for your radical reactions, you only use the half arrow, you only use the fish hook. Don't use a full arrow in any of these. And one final note about our radicals and radical stability. Not all radicals are as stable as each other. Free radicals, they don't have a formal charge, but they are unstable because they don't have an octet. And so the more electron density you can donate to that carbon, the more stable it becomes. So what that means is kind of the more methyl groups you have around it, those are groups that can donate electron density towards this radical to kind of help stabilize it a little bit. So methyl radicals are very unstable and very reactive. Radicals where there's 1 carbon group, those are a little more stable. Where we have 2 carbon groups, those are significantly more stable. And then if you have 3 carbon groups around it, that would be your most stable radical. And we'll see this again when we really get into our alkyl halide chapter. So you should be able, from this point on, to draw mechanisms for radical reactions.